To start, we'll open up Virtual Chem Lab, choose thermodynamics and enthalpy of the solution. So we'll open that up in the calorimeter lab. You can see over here in the balance there is your ammonium nitrate from this bottle here and your mass that you need to record in your data table, and then the ammonium nitrate is already weighed out on the paper for you. You can also see your coffee cup calorimeter on the bench that has water in it, and you want to make sure the stirring is on. So you can see here that it is stirring, and also this green light here is on for stir. So what you want to do now to have it start saving your data is to click on Save over here in the thermometer window. We're recording the temperature, and you just want to record for about 20 to 30 seconds just to get a baseline recording, and we'll measure the temperature of the water before we add the ammonium nitrate to see what happens. So it's been about 20 to 30 seconds, and so now we can just take the ammonium nitrate on the weigh paper and drag it over here, and it'll click into place, and you can drop it into the calorimeter. And then you're going to observe for another 20 to 30 seconds, and you can see what is happening to the temperature here. If you want to speed up time, you can certainly do that by pushing accelerate, and you can also watch the graph of the temperature and what is happening here. So you can observe if it's increasing or decreasing visually other than just looking at the numbers here. And once your numbers start to level off, so it's not getting any higher or lower, then you can just hit stop here. Then open your lab notebook and open this table here. And then you can record the temperature by scrolling down. So you want to look at the temperature, what it was for a while, and the different seconds here. So it's right around 25 degrees Celsius. And then the last temperature here is 23.67. So that's going to be your initial temperature was 25. Your final is 23.67. And those are the things that you need to record for part A. Alright, so here's some data that I recorded, and your data is going to look different than what I have here. These are just made up numbers, but I'm going to show you the calculations and how to do them. So in the first one was the mass that you recorded of ammonium nitrate before you started the experiment, and we need to convert that to moles. So that's that first box there. So that's 22.462 grams of NH4NO3. And if we want to convert this to moles, we have to get the molecular weight, which is 80 grams per mole. We want to get rid of the grams, so I'm going to put 1 mole on top, and this will be the 80.0 grams of NH4NO3. And then we can cross out our units here, and then we'll divide to get 0.281 moles. So I'm going to put that in my table. Okay, and then the mass of 100 mils of water, we can do that assuming the density of water equals 1 gram per mil. So for 100 mils of water, we'll have 100.0 grams. To determine the delta T, or the temperature change, it's going to be T initial minus T final. So this will be 22.6. Again, your values will be different. This is 10.2 degrees Celsius. So that is my delta T. So the change in Celsius is going to be the same thing as temperature change in Kelvin. So this would be also 10.2 K, because to convert from Celsius to Kelvin, you're adding 273.15 to get to that change there. The last thing that we have to calculate is Q, which is heat. And we'll come back to that table. So it's NH4 plus H2O. The reaction temperature decreased because it got colder, so that means that our heat is on this side. So it's going to be heat plus NH4 was absorbed, and so if it's positive, so this is an endothermic reaction, so our heat value is going to be positive, or enthalpy will be positive. Okay, and to calculate Q now, the equation in the introduction of the lab is that the mass of water times the specific heat of water, or times delta T, and this should be in Kelvin. So we have our mass of water from our table was 100.0 grams. The specific heat of water is a standard value. That's 4.184 joules per gram Kelvin, which is why we have our delta T in Kelvin. And our delta T is 10.2. So our units that cancel are grams and Kelvin, so we should just have joules left. So I have 4267.68 joules. So I'm going to put that in my table. Joules. The last thing we need to calculate is the molar heat of the solution in kilojoules. And to find the molar heat, it's going to be the value will be delta H equals Q that we just found over moles. So our Q is 4267.68 joules, and our number of moles is 0.281. Okay, this is 15187 joules per mole, and I need to convert it to kilojoules per mole, so I need to divide by 1,000. So this will be 15.2 kilojoules per mole. So for part B, we're going to go into thermodynamics again and choose heat of formation of aspirin, and we'll be in the calorimetry lab again, and you can see a different calorimeter now. This one is a bomb calorimeter, and the balance has already been tiered. So you want to record the mass of your aspirin. We need to assemble the calorimeter, and you want to just double click on these things in order. So first thing we want to click on is the cup on the balance pan, and then this bomb head. So notice that the cup is now here. Click on the bomb head, which moves it over to here. Click on the screw cap, and then the bomb itself. And then we click on the calorimeter to close the lid. All right, so these experiments can take some time, so we can speed up the clock by clicking accelerate. Notice that if you click it again, it will slow down. So clicking on it multiple times is not going to make it faster. There's a fast and then there's a slow. All right, so again, we're going to choose save to start saving our baseline information. So you want to do that for about 10 or 20 seconds. And on your lab clock here, that's been about 2 minutes. So then we can ignite and then watch the graph. So you can see how the temperature is changing. And again, once it starts to level off, then we can just click stop. So it looks like it's starting to level off. So I'm going to stop my data collection and open the lab book. This is the second calorimetry data. So I can see the initial temperature for heat of formation of salicylic acid. You are first asked to write a balanced chemical equation for the combustion of aspirin. So I'm going to do one for salicylic acid, which is the precursor for aspirin. So aspirin can be made from salicylic acid, and the formula is shown here. So in any combustion reaction, you react the carbon-containing compound with oxygen to form carbon dioxide and water. So I'm going to have C7H6O3 plus O2 will give us CO2 plus water. And you want to have a balanced equation, and right now my things aren't balanced. So I'm going to go to the process of balancing. So I'm going to do CHO. So I'm going to balance the carbons first. So on this side I have 7, and here I have 1. So I'm going to put 7 in front of here, and that will make the 7s. So I'm crossing out this one. Now I'm going to balance the hydrogens. On the left side I have 6. Over here I have 2, so I can balance that by putting a 3 over here. That should be H2O. Once I put the 3 here, I now have 6 hydrogens. And for oxygens on the left side, I have 3 plus 2 is 5. And over here I have 14, so 7 times 2 is 14. And then I have 3, so I have 17. So there's 17, and on this side I have 3 and 5. If I put a 7 out front of here, I have 14 plus 3 is 17. So my equation is balanced. So that would be the complete chemical equation for the combustion of salicylic acid, which is similar to the combustion of aspirin. So you would do the same thing but with your aspirin formula. The next thing you're asked to do is to write the combustion of aspirin in the form of the delta H combustion with the sum of the enthalpy of the products minus reactants. So our products are over here. This is reactants. So the next formula that we're going to use is delta H combustion equals the sum of N is our coefficient. This will be delta H for our products minus M is our coefficients for delta H of our reactants. So this would be the same as 7. 7 is from the CO2 of our products, and this is for CO2. And then we have to have our other product, which is water. So 3, which is our coefficient there. And then we're going to subtract our reactants now. And there's no coefficient on salicylic acid, so this will be just for the C7H6O3. 603. And then we're going to add 7 HF of the O2. All right, so that would be the equation that you would write for that. And we're going to use that in a little bit here. Here in this table, we have the mass of salicylic acid. And again, this is going to be different from your table because you have aspirin here. So we have salicylic acid, and then the moles of salicylic acid, we have to figure that out. And that would be 2.367 grams times 1 mole. And you're given the mass of aspirin, so you would put that down here. For salicylic acid, it's 138.12. So our grams get canceled out. And then we have 0.017 moles. And then for our delta T, here it's going to be the absolute value. So whatever you end up getting, we'll take the absolute value of that. So this would be 23.402. This will be 2.322 degrees Celsius, which is also 2.322 K. Okay, so to get our delta H combustion, this is C of the system, and I'm going to use the value for aspirin times delta T over N, which equals the moles. So C system is 10.310 kilojoules per K times my delta T, which is 2.322 K, and that is over the 0.017 moles. And our temperature increased. It went from 23 to 25, so my value of delta H is going to be negative. So this will be, when I calculate this out, negative 1379.5 kilojoules per mole. So our values of K canceled out, so we're just left with kilojoules per mole. Okay, the last calculation that you're asked to do is to calculate the heat of formation for aspirin given the standard enthalpies. And what you would need to do is use the equation from here. So this is the equation that we wrote earlier. And for the values of CO2, we're going to fill in, you would just substitute in the delta HF that is on the report sheet. So for CO2 in your report sheet, you have negative 393.5 kilojoules per mole for CO2. For water, the value is negative 285.83. And for O2, it's going to be 0. So you're going to do all that to find the value for aspirin. So I'm going to go ahead and use the values that are in your report just so you can see how to do it. But I'm going to use my coefficients. All right, so this will be 7. And I'm just going to put the values here that are from the report sheet. And the value that you would use for delta HF, that is the one that you just calculated on the last slide. So that's this negative 1379.5. Okay, and so now we would just fill in our value. So I have 7 times negative 393. And you want to remember to subtract there, and that's going to be the sum of these two numbers. So there's no coefficient, so this will just be the negative 1379.5, and that ended up being 0. So if you want, you can of course punch all these numbers into the calculator, but I kind of like to do it stepwise just so I can keep track of everything. So this is minus negative 1379. And I'll get negative 2246.5 kilojoules per mole.